All right, chapter 18 is going to look at the origin of life, so what we call abiogenesis, how living things came to be on Earth in the first place, and then also the early evolution. So, how did we go from these very simple organisms to the greater complexity that we see today? Specifically, we're going to look at the transition between prokaryote to eukaryote. Okay. So, just as a quick little reminder, in case you're unfamiliar, Big Bang Theory states that the Earth is about 13.5 billion years old. All of that matter, energy, everything coming from that singularity, universe is expanding. Various pieces of evidence to support this. We see that Earth is about 4.6 billion years old. We get this information from xenon krypton dating of zircon crystals that come out of Australia, some of the oldest rocks that can be found on our planet. Okay, so Earth is old. Okay, and so through time, we got all of these organisms, through various processes. So, conditions on early Earth here we've got early atmosphere, gases from volcanoes, very low in oxygen. It would have been almost entirely carbon dioxide and methane, carbon monoxide, nitrogen. These types of gases would have made up most of the atmosphere. Uh, Not a lot of oxygen, which is interesting because when we look at exoplanets, planets outside of our solar system, we look for signs of oxygen as signs of life because typically oxygen gas isn't formed through geologic processes. It's typically only formed biologically. So, interesting tidbit there. Rainwash minerals and salts out of rocks to form early seas. So we get these salty oceans with these various mineral components that existed there as well. So even early in Earth's history, after all the meteor impacts finished off and we got a solid atmosphere, we started to get these liquid oceans. This video here will look at some of those early conditions. Now, this is an artist rendering of what this would have looked like early on. We'd have had a lot of gases, these liquids turning into vapors, would have had a really active atmosphere weather wise because of all the energy that was coming into Earth from outside. So, when we're talking about living things, early in the semester, we talked about the building blocks of life. Okay, and so we've got these subunits. We've got amino acids that build up proteins, fatty acids that are going to make up our lipids, nucleotides, which make up our DNA and our RNA, and then our simple sugars, which are going to make up all the carbohydrates. So, in order to get to living things, we have to somehow get all of these organic molecules, these subunits, and then somehow put them together to get these living things. And what we see is that small organic molecules, these amino acids, fatty acids, nucleotides, these things can be formed by non living mechanisms, and we find them uh, throughout Earth. But then also, we see these things on extraterrestrial bodies like meteorites and asteroids and things like that, which is quite interesting. So we've observed and we've seen that we can get these monomers, these building blocks naturally without any living things being present. Okay. And so Miller, Stanley Miller and Urey did an experiment that showed we could get amino acids in various conditions that simulate lightning and what they thought Earth's early atmosphere would have looked like. And so we'll look at that. We've got Wachter, Schauser, and Huber found that amino acids could be made in a hydrothermal vent environment. So we'll take a look at that. And then amino acid sugars and nucleotide bases could have formed in interstellar clouds, so out in space, and then been brought to Earth on meteorites. And we do find these things when we look at asteroids and then on meteorites as well. we find some of these monomers. So this is the Miller-Urey experiment. And so this looks at creating amino acids in what they believed was early Earth's atmosphere. So we've got methane, ammonia, water, hydrogen gas. We've got some lightning to simulate storms that would have occurred early on in Earth's history. And then we've got water coming through here. And then what we see is this water, as we condense these gases, this water is going to contain these organic compounds, these amino acids. And so we, through this experiment, find that it is possible to get amino acids through this process. Now, the issue that some critics say that this experiment has is that there wouldn't have been any oxygen in the early atmosphere. So there wouldn't have been any ozone blocking some of that ultraviolet radiation. So this UV radiation would have destroyed ammonia and methane that existed in the atmosphere. And if we look back at this image here, ammonia and methane were two of the gases that they use simulated here. So without those gases, you're not going to be building these amino acids in this process. So it looks like at least the basic experiment that they use probably isn't representative of what happened. Okay? And so to build on this, scientists came up with the bubble model. So the ocean is constantly moving due to tides and the movement of water just kind of on its own. And we get these waves, and as they collapse over one another, we get bubbles. So the wind, waves, raindrops falling, volcanic action, both above the surface and under the surface, are going to create these bubbles in the water and on top of the water. And so when we do this, whatever is in that bubble, we get these gases in this area. And so they can happen a lot more quickly because they're more concentrated in this small volume. And then also these bubbles are going to give protection to these molecules that are formed from ultraviolet radiation. So if we get that ammonia and that methane trapped in these bubbles and we start building these monomers, they're now protected from being destroyed from this UV radiation. And so we see the bubble model here. And so this specifically shows the simulation with underwater volcanoes. So we get this eruption and we get all sorts of gases that are released from volcanoes here within these bubbles. We start getting reactions, start building organic molecules. If they can make it up to the surface, they'll pop, releasing into the air. And then we get ultraviolet radiation, lightning, other energy sources hitting these molecules, adding energy to allow larger molecules to form, as we see over here on the right. And then these get picked up by waves, raindrops bring them back down. And so we create these bubbles again. And so we can get further reactions, and this process can continue until we get larger and larger organic molecules through this process. Okay. And so this is one of the hypotheses of how this happened. Now, I will point out with most of these things with the origin of life, the experiments are difficult to do because we don't have a laboratory where life doesn't exist, right? It's hard to simulate this because life exists on Earth, and it's almost impossible to not have this type of contamination. Okay. But we can make simulations and we can do the best that we can in the lab to try and create these types of environments. This here is a hydrothermal vent. And we see that down here at the bottom of the ocean, where we're getting all of these gases coming up from Earth's mantle, is that we, with this energy and all of these gases pouring out, we see that amino acids and other monomers are being formed in these locations. Okay. I'm going to hit on the warm little ponds here in the next video.